athlete attempting a high jump. This style in high jump is known as the straddle technique and was dominant before 1968. At the Summer Olympics of 1968, Dick Fosbury of the USA introduced a new style of high jump, in which the athlete flipped the body over the bar. Later, all athletes started using this style, and it came to be known as the Fosbury flop. We can understand the advantage of this style by knowing the concept of center of gravity. You know that the weight of a body is the gravitational force acting on it. If m is the mass of a body and g is the acceleration due to gravity, then the weight of the body w is equal to mg. And it always acts in the downward direction towards the center of the earth. The line showing the direction of action of weight is known as the line of action of the weight of the body. If the body in consideration is a point mass, that is, a body of certain mass with negligible size, then the line of action of its weight passes through that point. The point mass can be balanced by applying a force equal to its weight acting upwards along the line of action. On the other hand, if the object is an extended body, then what will be the line of action of its weight? An extended body can be assumed to be made up of a large number of tiny particles. Each of these particles is attracted towards the center of the earth with a force equal to its weight. If W1, W2, and so on, Wn, represent the weights of these tiny particles, then they are parallel to each other and act in the downward direction. Such forces are called like parallel forces. When the weights of all these tiny particles are added, we get the weight of the whole body. Hence, we can write that the weight of the body W is equal to W1 plus W2 plus W3 and so on plus Wn. It means that W is a single resultant force that can effectively replace all the like parallel forces W1, W2 and so on up to Wn. The weight of a body is always seen to be acting through a particular point of the body. Even when the orientation of the body is changed, its weight always acts through this point. This point is called the center of gravity of the body and is usually represented by G. The center of gravity of an object is defined as a fixed point through which the entire weight of the object acts, irrespective of its position and orientation. A vertically downward line passing through the center of gravity of a body indicates the line of action of its weight. The body can be balanced by applying a force that is equal in magnitude to the weight of the body and acting through its center of gravity in the upward direction. Let us find the center of gravity. Let us find the center of gravity of some bodies. For a regular-shaped body with uniform mass distribution, the center of gravity coincides with its geometric center. For a uniform rod, the center of gravity is at its midpoint. For a rectangular thin sheet of uniform thickness, the center of gravity coincides with the point of intersection of the diagonals. In case of a circular ring, circular disc, or a sphere, their centers of gravity coincide with their geometric centers. For a right cylinder, G is at the midpoint of its axis. In case of a solid cone, the center of gravity is at a point on the axis and at a height h/4 from the base. Let us now find the center of mass of a triangular lamina ABC. Note that a lamina is a two-dimensional closed plane surface with mass. Identify the midpoints of each side and mark them as D, E, and F. Draw lines joining the three vertices to the midpoints of the opposite sides. These lines are known as medians. The point of intersection of the medians is called the centroid of the triangle, and it coincides with the center of gravity, G. Now let us find the center of gravity of an annular ring. Fix a wire AB along the diameter of the ring. Fix another wire CD along a different diameter of the ring. The intersecting point of these two wires represents the center of gravity of the annular ring. Let us now find the center of gravity of an irregular lamina. Make 3 holes A, B, and C in the lamina. Suspend the body from point A and using a plumb line, draw a vertical line AD. Now, suspend the body from point B and using a plumb line, draw a vertical line BE. Finally, suspend the lamina through point C and draw a vertical line CF using a plumb line. The point of intersection of the 3 lines AD, BE, and CF is the center of gravity of the irregular lamina. Note that the location of the center of gravity depends on the distribution of mass in the body. This can be best demonstrated by an example. Consider a hollow sphere. Its center of gravity coincides with its geometric center. Now, slowly pour water into the hollow sphere. As water accumulates, the lower half of the sphere water system becomes heavier. As a result, the center of gravity starts shifting downwards. When the water level is exactly half, the center of gravity of the sphere water system reaches its bottommost level. If you continue to pour water, the water level increases to the top half of the hollow sphere and, as a consequence, the center of gravity of the sphere water system starts rising. When the hollow sphere is completely filled with water, the center of gravity of the system coincides with the geometric center of the sphere again. The position of the center of gravity of a body need not always be within the body. For example, observe the system of 2 forks. This system of 2 forks can be balanced as shown. This is possible because the center of gravity of the system is outside it and is at the location shown. Let us now understand the advantage of a high jumper using the Fosbury flop. The maximum height reached by a high jumper depends on the strength and energy that they use at the time of launching their body into the air. Here, height means the height reached by the center of gravity of the high jumper and not the height of his body. The Fosbury flop enables a high jumper to send their center of gravity well below the bar as their body curls over and around it. This way, the athlete makes optimal use of their energy. Let us now learn about the center of mass of a body. The center of mass of a body is a point where the entire mass of the body can be assumed to be concentrated. For bodies of small size, the center of gravity coincides with the center of mass. Body of mass m tied to one end of a string of length r. Connect the other end of the string to a rotor. With the help of the rotor, the body can be made to execute uniform circular motion. The speed or the magnitude of the velocity of such a body executing uniform circular motion is constant. The direction of velocity at any instant is the direction in which the body tends to move if there is no external force acting on it. Observe the motion of the body if the string is cut when it is at A. The body moves along the tangent drawn to the circle at point A. Hence, the tangent drawn to the circle at any point gives the direction of velocity of the body at that point. When a body is executing uniform circular motion, the direction of the tangent, and consequently, the direction of velocity of the body, is changing continuously. Due to the continuous change in the direction of velocity, the body is said to be moving with some acceleration. The direction of this acceleration is always towards the center of the circular path and is called centripetal acceleration. The acceleration of a particle executing uniform circular motion is due to continuous change in the direction of its velocity and is always directed towards the center of the circle and is called centripetal acceleration. If the speed of the body is v and the radius of the circular path is r, then the magnitude of the centripetal acceleration, A, is given by the expression A is equal to v square by r. Let us understand the force responsible for the centripetal acceleration of a body in uniform circular motion. Consider a particle moving with uniform velocity along a straight line path. An external force acting on the particle causes a change in its velocity. If the force acting on the particle is in the direction of its motion, then the particle continues to move in the same direction with increasing speed. On the other hand, if the force is acting perpendicular to the motion of the particle, then there will be no change in the speed of the particle, but it will be deflected from its straight line path. This makes the particle move along a curved path. If the force continues to be normal to the motion of the particle at every point of its path, then the particle moves along a circular path with constant speed. A force that is normal to the velocity and continuously acting on a particle, making it travel along a circular path, is called centripetal force. This force is responsible for the centripetal acceleration of the body. According to Newton's second law of motion, net force on any body is equal to the product of its mass and acceleration. Since centripetal acceleration A is equal to v square by r, centripetal force F is equal to mv square by r. If the angular velocity of the particle is omega, then linear velocity v is equal to omega into r. Then centripetal force is also equal to m into omega square r. Let us now consider some examples of bodies in uniform circular motion and the centripetal forces acting on them. The moon revolving around the earth is in uniform circular motion. The required centripetal force is provided by the gravitational attractive force of the earth. We also know that in an atom, electrons revolve around the nucleus. The electrostatic attractive force acting on the electrons provides the required centripetal force. Now, consider a platform rotating at constant angular velocity. For smaller values of angular velocities, a body placed on it exhibits uniform circular motion. The friction between the surface and the body provides the required centripetal force. Before we study uniform circular motion further, let us now understand the concept of frame of reference. Look at Sarita. She is standing on the banks of a river, observing the water flowing, and the wooden planks floating on and the boats sailing in the water. If she wants to measure the speed of the boat, she has to find the location of the boat at two different instances. In order to find the location of the boat, she needs a coordinate system. She also needs a clock to note the time taken by the boat to move from one position to another. A coordinate system fixed to the observer with a clock attached is called a frame of reference. In this case, Sarita is the observer. The observations made by Sarita will depend on the motion of her frame of reference. First, consider the case when Sarita and the frame of reference attached to her are at rest with respect to the ground. She observes the wooden plank moving along the river water with a speed equal to the speed of water. She also finds that the boat is moving at a rate faster than that of the river water. Let us now attach the reference frame to the wooden plank. Let us see how Sarita observes the surroundings when her frame of reference is attached to the wooden plank. The frame of reference is now moving with some velocity with respect to the ground. Now, Sarita finds the river water to be at rest and the boat moving at a slower speed. More interestingly, she observes the banks of the river moving backwards. If the frame of reference is attached to the boat, the observations will be as shown here. The variation in the observations is because of the motion of the frame of reference. In the first case, the observer is in a frame of reference, that is, at rest. In the subsequent cases, she is in a frame of reference, that is, moving with uniform velocity. A frame of reference that is at rest or moving with uniform velocity is called an inertial frame of reference. It is very important to note that Newton's laws of motion are valid only in an inertial frame of reference. To understand this aspect, let us consider a boy on roller skates standing on an empty passenger car. Let us assume that the observer and the frame of reference are attached to the passenger car. When the passenger car is either at rest or moving with uniform velocity, the boy is at rest with respect to the frame of reference attached to it. As the boy is on roller skates, the frictional force between him and the surface is negligible, and hence the net force acting on him is also negligible. When there is no net external force acting, according to Newton's first law of motion, the boy must be at rest with respect to the frame of reference. Hence, we can conclude that Newton's laws are valid in case of inertial frames of reference. What happens if the passenger car starts accelerating? When the car, which is initially at rest, starts moving forward with some acceleration, the observer attached to the car finds the boy moving with the same acceleration in the opposite direction. This is strange. As discussed earlier, there is no net external force acting on the boy. Still, the boy is found to be accelerating by an observer. This acceleration cannot be explained by Newton's laws of motion. In fact, the problem here is the accelerating frame of reference of the observer, where Newton's laws do not hold good. An accelerating frame of reference, where Newton's laws of motion are not valid, is known as a non-inertial frame of reference. Let us find how another observer, whose frame of reference is attached to the ground, describes the motion of the boy. The frame of reference of the second observer is at rest and is an inertial frame of reference. The second observer finds the car leaving the boy. Since the friction acting on the boy is negligible, the boy tends to be at rest due to inertia, while the car is accelerating. Hence, we can conclude that Newton's laws hold good only in an inertial frame of reference. In order to use Newton's laws of motion in a non-inertial frame of reference, a pseudo-force needs to be considered. This pseudo-force is equal to the product of the mass of the body and the acceleration of the non-inertial reference frame. The force needs to be taken in a direction opposite to the direction of the acceleration of the frame of reference. A frame of reference attached to a rotating body is also a non-inertial frame of reference because of its centripetal acceleration. The pseudo-force associated with a rotating non-inertial frame of reference is called centrifugal force. The magnitude of centrifugal force is equal to that of centripetal force and is equal to m omega square r. Centrifugal force means a force that is fleeing away from the center. The direction of centrifugal force is opposite to that of centripetal force. Note that centrifugal force is not a reaction force to the centripetal force, as both the forces are acting on the same body. Let us learn about some applications of centrifugal force. A centrifuge is a device in which solid or liquid particles of different densities are separated by rotating them in a tube in a horizontal circle. The centrifuge used in a laboratory is as shown. Small test tubes containing a mixture of liquids with different densities are made to rotate in a horizontal plane at high speed. The liquid in the test tube is a mixture of different densities. The particles of a high-density liquid have more mass than the particles of a low-density liquid. When two particles of different masses are at the same distance from the axis of rotation, the centrifugal force acting on the particle with the greater mass is larger. As a result, the dense particles tend to move along the length of the tube to a greater radius of rotation, displacing the lighter particles to the other end. In this way, particles of different densities are separated by the centrifuge. The domestic churner or milk skimmer also works on the same principle. When milk or buttermilk is made to rotate, the particles of higher mass are thrown away and the particles of cream settle at the center. A laundry dryer or centrifugal drying machine contains a cylindrical vessel that can be rotated at high speed about its own axis. When the vessel with wet clothes is rotated at high speeds, water is forced out of the perforated walls due to centrifugal force. Another device that works on centrifugal force is the governor of a heat engine. This device is used to control the speed of an engine by controlling the amount of fuel injected into it. Large quantities of liquids at low pressure can be moved through pipes using a device called the centrifugal pump. Centrifugal force is also used in blowers. In a circular path at a constant speed. It is said to be in uniform circular motion. As the body is continuously changing its direction of motion, its velocity changes continuously. Since the velocity of the body is changing, it has acceleration, which is known as centripetal acceleration. Let us find the magnitude and direction of the centripetal acceleration. Here, r and r' are the position vectors, and v and v' are the velocities of the body at points P and P'. As the body is moving in the circular path, the velocity vectors will be tangential to the circle at the points P and P'. The change in velocity, delta V, is obtained by using the triangle law of vector addition. V and R, as well as V' and R' are perpendicular to each other as V and V' are tangential to the circle, and R and R' are the radii of the circle. Therefore, delta V is perpendicular to delta R. If we place delta V along the line which bisects the angle between R and R', the arrow of delta V points towards the center of the circle O. The average acceleration acts along delta V. Therefore, average acceleration E bar is directed towards the center of the circle. We can verify all these by changing the position of the point P dash. As delta t tends to 0, the angle delta theta also tends to 0, and hence the average acceleration becomes instant acceleration. Therefore, we can conclude that the acceleration of a body in uniform circular motion is always directed towards the center of the circle. Now let us find the magnitude of the acceleration. As you know, the angle between r and r dash is delta theta. As v and v dash are perpendicular to r and r dash, the angle between v and v dash is also delta theta. Therefore, triangle OPP dash formed by the position vectors and triangle ABC formed by the velocity vectors are similar. From these similar triangles, we can write magnitude of delta V by V is equal to magnitude of delta R by R, where R is the radius of the circle. This can be written as magnitude of delta V is equal to V into magnitude of delta R by R. Magnitude of A is equal to limit delta t approaches to 0. Magnitude of delta V by delta t, which is equal to limit delta t approaches to 0. V into magnitude of delta R by R delta t. This expression can be written as magnitude of A is equal to V by R into limit delta t approaches to 0, magnitude of delta R by delta t. Let this be equation 1. As delta t approaches 0, delta theta also approaches 0. Arc PP dash is approximately equal to PP dash, which is equal to magnitude of delta R. Magnitude of delta R is approximately equal to V delta t. This can be written as magnitude of delta R by delta t is approximately equal to V, which implies limit delta t approaches 0, magnitude of delta R by delta t is equal to V. Let this be equation 2. Substituting equation 2 in 1 and by simplifying, we get A is equal to V square by R. Let this be equation 3. The acceleration of a body moving with a constant speed v in a circle of radius r has a magnitude v square by r, and it always acts radially directed towards the center of the circle. This acceleration is called centripetal acceleration. The word centripetal refers to center seeking. Now, let us find the centripetal acceleration in terms of angular velocity, omega. As the body moves from P to P dash in time delta t, the line OP turns through an angle delta theta. As you know, omega is equal to delta theta by delta t. Let this be equation 4. V is equal to arc length PP dash by delta t, which is equal to delta S by delta t. Let this be equation 5. Delta S is the arc length, which is r delta theta. Let this be equation 6. Substituting 6 in 5, we get V is equal to R delta theta by delta T. Let this be equation 7. Substituting 4 in 7, we get V is equal to R omega. Let this be equation 8. Now, substituting equation 3 in 8, we get centripetal acceleration AC is equal to omega square into R. Now let us find the centripetal acceleration in terms of frequency. Time taken to make one revolution, that is, time period is T. Frequency, F, is the number of revolutions in 1 second. Therefore, F is equal to 1 by T. Distance moved by the body in one revolution is equal to 2 pi r. V is equal to 2 pi r by T. On substitution, we get V is equal to 2 pi rf. Omega is equal to 2 pi f. Substituting the values in equation 3, we get AC is equal to 4 pi square f square into r. According to the law 42 of the laws of cricket, the bowling of fast short-pitch balls is dangerous and unfair if they are likely to inflict physical injury on the striker, irrespective of the protective equipment he may be wearing. How could a small object like a ball inflict injury on a cricketer? The impact of a moving object differs based on its momentum, which is the product of the body's mass and velocity. A cricket bowling technique devised in the 1930s called body line involved aiming fast-paced balls at the shoulders of the batsman. In the past, many batsmen have been injured due to the impact of balls travelling with high momentum. In this lesson, you will learn about momentum and the second law of motion. At the end of this lesson, you will be able to identify the significance of momentum, state Newton's second law of motion, derive the expression for the measurement of force, and explain the impact of change in momentum in terms of impulse. To analyze the concept of momentum, let's compare the impact of moving objects in different situations. Observe the marble dropped onto the thin glass pane below. The glass pane is intact. But what happens if we drop a cricket ball onto this glass from the same height? Ouch! The glass pane shattered. Why did the glass pane shatter this time? What was different in the two situations? The height from which the marble and the ball were dropped was the same. So was the velocity of both the objects when they struck the pane. Clearly, it must be the bigger mass of the cricket ball that made a difference. As the mass of the cricket ball is more than that of the marble, its impact on the glass pane is higher than that of the marble, and thus it shattered the glass pane. Let's now look at another case where two identical marbles, say P and Q, are dropped onto a thin glass pane from different heights. First, we drop the marble P on a thin glass pane from a height of 1 meter. The marble P does not damage the glass pane. Now we drop another marble Q from a greater height. Wow! Dropped from a greater height, even this small marble has shattered the glass pane. Why was the glass pane shattered by the marble Q and not by the marble P, even though the mass of both the marbles is the same? As the height from which an object is dropped increases, the velocity with which it strikes the ground or any other reference level also increases. Being dropped from a greater height, the velocity at which the marble Q strikes the glass pane is greater than that of B. Hence, the impact of marble Q on the glass pane is greater than that of B. That's the reason marble Q shattered the glass pane while marble P did not have much impact on the glass pane. Based on these observations, we can say that the impact of any object on the other depends on two factors of the object causing the impact, namely, its mass and velocity. These two factors together constitute a physical quantity, called the momentum of a moving object. The momentum of an object is the product of its mass, m, and its velocity, v. It is denoted by the small letter p. Thus, you can express momentum as P is equal to mv. Momentum is a vector quantity. It is measured in kilogram meter per second or Newton second in the SI system and in gram centimeter per second or dyne second in the CGS system. Because of its momentum, a fast-paced cricket ball can hit and hurt the batsman or the wicket-keeper if the batsman is not able to play the ball properly. That's why batsmen on the cricket field wear protective helmets and body pads to prevent possible injury. Momentum helps us understand the impact of collisions and explosions. For example, it explains the impact of a collision between two trucks or a cannon firing. The greater the momentum of an object, the larger the impact is on the other object. Remember period films where we often saw columns of armies who used huge logs to break down the gates of a fort. The group of men holding the log goes back a fair distance from the gate. Then they run to the gate to ram the log into the gate for maximum impact. The velocity and the mass of the log together provide enough momentum to break the gates down. The momentum of this army column differs at different points in their run-up to the gate. Although the mass of the log is constant, their velocity is increasing constantly. That is, they are accelerating. Another example is when actors in movies perform stunts, such as breaking down a door. The momentum of an object increases when it accelerates. Therefore, the rate of change of momentum depends on the acceleration of the object. Newton's second law of motion states that the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction of the applied force. Let's verify this law using an example. Observe this billiard table. The yellow ball is at rest right now. However, when the cue ball hits the yellow ball, it is set into motion. After being hit, the cue ball moves with less velocity, while the yellow ball moves with more velocity. Thus, there is a change in velocity of both the balls, that is, a change in their momentum. Additionally, the direction of motion of the yellow ball is the same as the direction of motion of the cue ball. Now let's observe what happens when the cue hits the yellow ball with more force. As you can see, the yellow ball now moves a longer distance than the last time, before coming to rest again. Thus, when the force applied by the cue ball increases, the momentum of the ball increases as well. Hence, we can say that the rate of change in momentum of an object is proportional to the force applied on it. A lot of our actions are based on the second law of motion. Observe the cricket fielder reaching out to catch a fast-moving ball. As you can see, he pulls his hands back to catch the ball. Why does he do that? He does that to reduce the impact of the fast-moving ball on his hands before bringing its velocity down to zero. By pulling his hand back, he increases the duration of time taken in bringing the velocity of the ball to zero. Newton's second law of motion can be expressed mathematically as F is equal to ma, where F is the force applied on a body, measured in Newton in the SI system and in dyne in the CGS system. M is the mass of the body, and A is the acceleration produced in the body. Let's derive this relationship using an example. Consider a ball of mass m having an initial velocity u. When a force of magnitude F is applied on the ball for time t, the ball moves ahead with an acceleration a. In the time period t, the ball accelerates to a final velocity v. Let P1 be the initial momentum and P2 be the final momentum of the ball. By the definition of momentum, P1 is equal to mu. P2 is equal to mv. Hence, the change in momentum is P2 minus P1 is equal to mv minus mu, or m multiplied by v minus u. The rate of change of momentum is the ratio of change in momentum to time. That is, m multiplied by v minus u divided by t. According to Newton's second law of motion, the rate of change of momentum is proportional to the force applied. This gives us the relationship F is proportional to m v minus u divided by t. The acceleration a of the ball is the ratio of change of velocity v minus u to time t. Hence, we can write this relationship as F is proportional to ma. We use a constant of proportionality, k, to equate this relationship. Therefore, F is equal to kma. In the SI system, a unit force is a force with a magnitude of 1 Newton. Unit force is defined as a force that produces unit acceleration, that is, 1 meter per second square, when applied on a body of unit mass 1 kilogram. Thus, substituting the values in the expression, F is equal to kma, and simplifying, we get the value of k as 1. Hence, we get the mathematical expression of the second law of motion as F is equal to ma. Therefore, according to second law of motion, you can express the force applied as the product of mass and acceleration of the body. Using the expression for second law of motion, we can define the relationship between the SI unit of force, Newton, and the CGS unit, dyne. Consider unit values for force, mass, and acceleration of an object, and substitute these values in expression F is equal to ma. You get 1 Newton is equal to 1 kilogram meter per second square. Since 1 kilogram equals 1000 gram and 1 meter equals 100 centimeter, 1 Newton is equal to 10 raised to the power 5 gram centimeter per second square. Since 1 dyne is equal to 1 gram centimeter per second square, 1 Newton is equal to 10 raised to the power 5 dyne. Let's again look at the second law of motion. According to this law, force equals rate of change in momentum. Rearranging the expression, change in momentum equals product of force and time. When a large amount of force acts on an object in a very short duration of time, it is termed as impulse. Here is an example of a situation where we see impulse at work. Consider a cricket ball bowled towards a batsman in a cricket field. The batsman strikes the ball with a large force that acts on the ball for a moment. The impact of the bat enables the ball to change its velocity in magnitude as well as direction. This is the impulse of the bat on the ball. Impulse is numerically equal to the change in momentum. Impulse is denoted by J and is measured as a product of force and time. As the impulse of a body is numerically equal to change in its momentum, the unit of impulse can also be expressed by the unit of momentum. Thus, the SI and CGS unit of impulse are Newton second and dyne second respectively. In karate, a man can break a brick with his bare hands, even though the mass of his hand is small. The high acceleration of the strike provides enough force of high magnitude to his hand to break the bricks. This large force acts on the brick for a short duration, making an impulse. This impulse helps to break the bricks. This brings us to the end of this lesson on momentum and the second law of motion. Hope this session provided you with an understanding of the concept of momentum and Newton's second law of motion. Now you can use the mathematical expression for force to solve problems in physics. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.